And welcome to SanfordFlipMath. We are doing a little review session. We're just recording for the sake of those that are not able to be here during seminar. And this is stuff correlating with the Finney, Demana, Kennedy calculus book. And we are wrapping up chapter 4. Test is tomorrow, and we're just kind of hitting some problems as needed. This is live in front of actual humans, so if the recording is a little goofy, then that's because we're a little goofy. All right. All right. Yeah. Shout out to Darby. All right. There it is. Yes. Yes, ma'am. Yes, Kira. 4.0.5. So this corresponds to the little practice test we've been working with lots of creative numbering here. 4.0.5. It's an open top box made from a rectangle that is 10 inches by 14 inches. This is our throwback problem to the last unit. And we want to maximize volume for an open top box. And again, the idea is we're cutting out squares from the corners, and then we're going to fold it up. And the question actually asks us for what is the maximum volume possible. Okay, so not just what size squares do we cut. It's not asking for the dimensions, although all of that stuff is useful. So, all right. So the picture again, and I know we've seen this kind of problem like probably half a dozen times. We even saw it a little bit in pre-calculus. But the idea is as I cut those squares out of the corners, I can then fold up the sides. And so we end up with a box that looks something like this. And if this was my 14, then this is 14 what? 14x? I'm actually subtracting x from each end, so minus 2x, and then going along this side, 10 minus 2x, and then the height of this box is, no, we don't. We're going to call it x. Okay? So volume, no, this is a rectangular prism. This is like a box. Okay, so, yep.
Why is it minus?
Again, the idea is that if I take this rectangle and I'm cutting a little square out of the corner, so that little square is gone, and I do that on both ends. It's all good, I got it. Trained professional. Something like that. All right, so the idea is I cut off x on this end and I cut off this x on this end. I'm going to fold that up. I'm going to fold those sides up too. I've cut off x from both ends. That's 1x and another x. That's 2x's I've cut off. So I got 14 minus 2x, 10 minus 2x, and x. So volume is length times width times height. And it doesn't matter which order is which, it doesn't matter which one's which. And now I want to maximize this quantity. Well, how do I maximize a quantity with calculus? You mean multiplied it out? You've distributed it, you foiled it. Factor it is when you take it apart.
Yeah, I'm sorry.
Yep. Yeah, no, that's good. I would do that. So here's the thought process. To find a maximum or a minimum, we want to look at critical points and endpoints. Well, critical points are where the derivative equals 0 or the derivative doesn't exist. Endpoints are where things stop making sense, or we have breaks in the graph, or we have, any place there's a corner or a cusp, or maybe it doesn't make sense for the context. Okay, so to do the derivative equals 0, it makes sense to do the derivative. And the easiest way to do the derivative is to multiply this mess out. So that's what I'm going to do. So I need to distribute, so 140. I'm going to save the x for the end. We'll do the x after this. Okay, so outer is going to be minus 28x. Inner is minus 20x plus 4x squared. This is still times x. Okay, we're going to combine like terms and distribute. So this is going to be 140x. This is minus 48x. And again, I'm distributing. So I'm going to say minus 48x squared. I'm just combining a step here. Plus 4x cubed. And again, this is the volume equation. I haven't done a derivative yet. This is just volume at this point. Yes, sir. Steve, did you have a question?
Yeah. Oh no. When you're done with this.
Okay. All right. So we again want the derivative equal to 0. Well, the derivative with respect to x, v prime, 140 minus 96x plus 12x squared. So we need to make this equal to 0 and solve it. Well, that looks like a jacked up mess. In there somewhere. Yeah, you could do quadratic formula if you want. 96. I'm just looking for ways to make this easier. I don't think 140 divides by 12 evenly. It does not. 4. I'm just looking for ways to make life a little bit easier. If I divide both sides by 4, I'm just thinking smaller numbers are easier. So this will be 35 minus, is that 24? And I think I got the next one myself. Thank you. You want quadratic formula or you want to play with factoring? I'm going to flip it. Oop, 35. Ah. Because it made a mess out of 140. I tried it. In the calculator, I did 140 divided by 12 just to see, but 12 is a factor of 3 and 140 doesn't. So it makes a decimal, and I don't really want to do that. All right, so it feels weird going to the left, but that's where we're going to go. Let's try factoring. Signs have to be the same. They have to be minus. I need factors of 35, so probably something to do with 5 and 7. Doubt it's going to be 1 and 35. I'm going to go 7 here and 5 here. I don't know if that's going to work. 21, nope. I don't know, is this going to work? Does this factor? I don't remember. About to find, you have I have an app for that. What? 22, seems like I'm all around it. All right, let's just double check I didn't make a boo-boo. That looks like, that's right, okay. I know, what? She's cheating. That's awesome. I want that. I want that app. No. Now, if you can program your calculator, there are programs out there that'll do it. Yeah. Seriously? Pardon me. That was funny. Siri can do that seriously? Sorry. All right, opposite of negative 24. Plus or minus the square root of negative 24 squared minus 4 times 3 times 35 all over. I mean, if it works, then it's awesome. If not, then, all right, it's time to move on. All right, so 24 squared minus 12 times 35, so 156. I don't think 156 is a perfect square, so. It's divisible by 4. No, that's it. Well, how else you going to get it? 2 goes into all of these. Yeah. Welcome to Algebra 1. Yeah, yes, you need to know the quadratic formula. It was the opposite of the negative. Right, it's the opposite of b. Remember you memorized the quadratic formula as you just said. Well, it's the negative of the negative. You can say negative b, negative of negative 24. Ah, there it is. Uh-huh. It didn't work. I needed to get 24 out of this for the middle term, and this was negative 20, I'm sorry, this is negative 7x, and this is negative 15x, which was negative 22. Sorry, I should have crossed it out a long time ago. It didn't work. Okay. All right, so 12 plus the square root of 39. Let's just do a little mental math here for a second. Well, we can do this to the nearest, we can round this. Why don't we just do it? We won't do it mental, we'll do it calculator. So 12, okay, so I'm going to do parentheses so I can do this over again. 12 plus the square root of 39. Uh-huh. Yes. It's probably called something clever like quadratic formula program or something. And no, it's not standard, but you can find it online though, and then just download it to your calculator and stuff like that. As far as on an AP Calc test, you could have that. Sure you can. You could have a TI-89.
That's what I was thinking. Like, can you use that on the ACT?
Officially, I don't believe you can.
Officially.
I mean, they don't check that stuff though, so I don't know. I don't know. You know, as far as programs on the ACT and stuff like that, I don't. How do they? I don't know how they would control it. Well, and they say specifically that there's no requirement to reset calculators either. So, all right. So those are my two x values. Now, so here's my question: do both of those make sense? I don't know. Now one of these is 1.9 something. Well, 14 minus 2 times 1.9, that gives us a number that makes sense. 10 minus 2 times 1.9 something, that's fine. And a height of 1.9 something is fine. Okay. In terms of the 6.08, yeah, if I put 6.08 here, I'm going to have 2 times 6-ish is 12. 10 minus 12 would make it negative. So the 6 is out. This thing is out. It's a perfectly valid solution for our equation. It just doesn't make sense for the context. Okay, now back to the question that this problem asked. Excuse me. What were we supposed to do? Find the maximum volume. What have we found? We found x. We found the height. So you need to plug it in. Okay, so now you can plug it into whichever version of the volume you want. You could plug it into this. You can plug it into this. You could just plug it into these sides and do this. It doesn't matter, but you need to plug it into one of those. Okay, so I'm going to do a little typing here. Okay, so I'm going to go back to, I think, well, it doesn't really matter. I guess I'll do the one that's 140x. So 140 times my last answer minus 48 times my last answer squared plus 4 times my last answer cubed. Okay, so that's how I type that in. Is that real? 120-ish? Is that right? Seems not huge enough, but I guess it's probably fine. 120.164. This was meters originally? Was it? Okay, let me just double check. I want to make sure. Oh, I can't check here because I didn't write it down. Inches. Okay, then I'll dot my M. And there we go. Okay, and remember this is volume, so it's cubic.
Wait, so you plugged in 1.9
Mm-hmm.
that equation, and then that
Into the volume equation. It should be into any version of the volume equation.
So can we do parabola equation?
Which one? That was 4.0.5, right? Sweet. Yeah, that's what I got. Awesome. All right, so we want the green on green. That's always such a clever move, Sanford. All right, which one are we saying? 4.5.5. Rectangle is inscribed in the parabola. That's 4.5.5. That's an optimization problem.
One of our recent parabola problems. It's not on this one.
So we're talking about rate of change on the parabola kind of thing.
In the angle that you look at the angle.
So there aren't any like that on here? I'm shocked. Oh, it's just a little different. All right. On the second practice test. Am I? All right, what's your issue?
Okay, I get everything from number one, except for how you talk, how come the slope is not 4tan 3x, it's only 4.
All right, from the very first practice test. All right, so just a quick little note. You are told that, okay, so again, this is number one from the first practice test. You are told that f prime is 4 tangent 3x. We're supposed to be doing the linearization at x equals pi over 12. You're also told f of pi over 12 is 3. Please pay attention to notation here, because sometimes people get in a hurry and they'll think this is the original equation. And in the immortal words of Sanford, that ain't it. Right? This is the derivative of that. So this is really just for slope. Yep. Because if I hold the marker, it thinks that I'm still doing something, because it's missing. And I can move that one there, and now it's red. Isn't that exciting? So you can watch that at home later, and you think, what is that guy doing? Yeah, well, you don't. All right, so your question is really about slope.
Yes.
All right, so here it is, slope. Put that in. That's it. Plug it in, plug it in. We're going to find f. Yes, so we're just doing, this is already derivative. Okay, so 4 times the tangent, really, of pi over 4. Well, what's the tangent of 45 degrees? It's 1, equal rise and run. Okay, so already I know it's going to be y minus the y value equals the slope times x minus the x value, and we know for linearizations we want y equals. And I'm done with A right now. Now, and part B just said put in a value for x and calculate it. Yeah, so you're going to put it in right in that x is 0.3, and you're going to use that to do an approximation. Now, technically, let me be a little technical. This is an approximation for y. That was funny. Shh. Okay, folks. This is an approximation for y, because what we're doing is looking at the equation of a line near that point. That's what a linearization does, is we use the equation of a line to approximate the function near a point. We have to be near that point. The farther away from that point we get, the more off our approximation is. Yes, ma'am?
Okay, so you know when we take the test, do we have to do the approximation?
You really should do the approximation sign.
So,
Yeah.
If you do the approximation sign, you will not lose points.
All right.
That depends on how mean I want to be that day.
okay, so Mr. Sanford,
Yes.
it's a percent, one of those percent error problems.
Yeah.
How do you do that?
You set up a relative error or relative change. dv over v equals something times dr over r, or dv over v or dA over a equals.
Can you do an example?
Sure. I thought we were doing a related rates problem on a graph.
Do that one first.
The related rates problem on a graph? Sure. I don't know. I am told that there's one on the second practice test, and there it is, number 5. Okay, so this is the second practice test. We have a particle moving on. Yes. And we are told, and this is in centimeters supposedly, we are told that dx dt, wasn't that nice of me to tell you this was dx dt? That's so unlike me. And it says, what is the rate of its change of its angle with the x-axis? Okay, so let's get a little context going here, a little situational awareness of what's going on. Oh, when x is 3, it says. Okay. All right, so here's the situation. Okay. They're going to love that on the video.
I'm sorry. Okay, so
It's all good.
I was looking at two different private problems, and one was saying when x is 0, and another one
Well, it depends on, now, the when is a different question. You know, like if it's saying, how is its, you know, what is its rate of change for its distance from the origin, that's really saying, I want dr dt.
Yeah, and then there's another one, and you just basically use the formula, the derivative of that formula. So that's just saying.
That was asking about dy dt, rate of change of the y value, right? So if you can take what it's asking you and put it into symbols, it should help guide you as to what you need to know.
Finding dy is just finding the derivative of the equation, but
Right.
finding the rate of change, that's what
Rate of change of what? All of these are rate of change.
rate of change of the distance between the 2 points.
If I'm talking a rate of change between the distance of between 2 points, now I need a triangle. I have an x, I have a y. Hang on, I'm being interrupted. Okay, so if this problem is not looking for the rate of change of that length, of that distance. But if it was, that's where we'd be doing all that triangle stuff that you were talking about, right? All right, so let me get that out of there because it does not apply to this. Okay, now in this case, it does apply to a triangle. There is a triangle involved, but really it's about the angle it said made with the x-axis. Okay, so I know that we're talking about when x is 3 at some point. I'm really not there yet, but I'll put it here just so we know exactly, have an idea what we're talking about. Okay, so what we're actually talking about is this angle. It wants to know, how is that angle changing? Well, that angle isn't even in here. So I need a way to make an equation that has theta in it. So that's the issue. Well, I'm going to put some more labeling on this. This distance is y. This distance is x. Tell me what I can do to put together an equation that's about theta. I think you want to do tangent of theta. So tangent of theta is opposite over adjacent, right? How do I know to use tangent? Well, I need something that's got theta involved, and that's the easiest one to do is x and y. Anything else, I have to do a Pythagorean theorem to get the r value, that distance, and I don't want it. Okay? Yep. Okay, so we ultimately want to know the rate of change of theta, so we need to involve theta, and so that's why we brought the tangent in here. Okay, so again, we're just looking for a way to involve theta somehow. Well, I think we have too many variables going on, so I'm going to replace y with 10x minus x squared. Nope. I don't need a y though. That's okay. I can do the derivative of the left side with a d theta dt and derivative of the right side with a dx dt. It's all good. Now, I can clean this up a little bit and make my life just a smidge easier. As it stands right now, I'd have to do a quotient rule, and honestly, I'm not that excited about the quotient rule. So I got an x in every single term. I can divide 10x divided by x is 10. X squared divided by x is x. That's going to be an easy derivative now. All right, so here we go. Tangent of theta. What's the derivative of the tangent? So secant squared theta d theta dt equals derivative of 10, 0. Derivative of negative x, negative 1 dx dt. Don't forget the little d something dt's. All right, now it's plug and jug time. Did they give me dx dt? They did. It's negative 1. Love it. So negative 1 times, you guessed it, negative 1. Now we need to do secant squared of theta. Yep, right here. dx dt was given as negative 1. Yep. Okay, so now what do you do about the secant squared of theta? When x is 3, so x is 3. What's y? Okay, so 10 times 3 minus 3 squared is, you guessed it, 21. If I do a little Pythagorean theorem, then I can do cosine, which I can flip and make that secant. right? Because ultimately, I don't really care what the angle is. What I care is, what I really want is secant squared. Okay, so secant, well, that's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is the reciprocal of that. So secant squared will be that squared. Right? Secant's the reciprocal of cosine, so secant is hypotenuse over adjacent. And then I really want secant squared, so I'm going to square the hypotenuse over adjacent.
But wait, but what you do, aren't you going to basically divide that, so it's just going to be 1 over secant, so it's really going to be cosine?
That's true. I mean, if you want to make it equal to cosine squared now, I mean, we can do that. All right, so let me write down what just happened, because I know somebody's going to be looking up going, wait, what just happened? So let's write it down. Okay, secant squared is 1 over cosine, and I didn't even say Jordan's name. Oh, never mind. So far, so good? All right, so I'm going to multiply both sides. That was awesome. So this is just 1 times cosine squared, right? So I need to find out cosine and square it. And then we're done. I'm just going to go ahead and do it. I was going to find cosine squared, or secant squared first and then play with it, but I like this. This is good. Sorry, did that mess up your plan? It'll still work. All right, so I need to know the hypotenuse. You can rearrange it any way you want, as long as you're doing legitimate algebra. This is 9. This is 441, isn't it? Sure it is. Isn't that cool? 21, 21? 21 times 21? I believe it's 441. Somebody ought to check that. Isn't that funny? That's cool.
Oh, so there's a pattern in the squares, isn't there?
Okay, and obviously we're not worried about the negative version of that. Thank you. All right, so let us take this. No, so adjacent's 3. Hypotenuse is the square root of 450. All right, so adjacent is 3. Square root of 450 for hypotenuse. So I'm going to square this whole thing. Just about there. I'm quite excited. So this is going to be 9 over 450, which reduces to 1 over 50. What about units? How do you know? Centimeters? So the angle's changing in centimeters? Why radians? Because it's calculus. Hello. Yep. That's bad. Don't get it wrong. Just do it. Yeah, if it's sine or cosine or if you did the derivative, if you're doing calculus with trig functions, then it's radians. Yep. I don't know. I didn't do my calculator, but sure. Yeah. Yep. Well, I ultimately didn't end up using this because Alex had it. There's her shout out. Alex was talking about Alex Swift. All right, are we going to do calculus? Thank you. Thank you, Malik. All right, so ultimately, Alex suggested we multiply both sides by cosine squared here to make it about cosine anyway, so we could get d theta dt by itself. So I didn't end up even using it. I mean, it's true. Secant's the reciprocal of cosine. So instead of adjacent over hypotenuse, it's hypotenuse over adjacent. Well, I was going to use it, and then Alex suggested we do it this other way. All right, just a quick note. If the problem specified any kind of units, then please make sure you get it to the correct units. Okay, I don't think that was it, right? Okay, and even though we couldn't get Ashana or Chima to do this problem for us, they were here. Thanks for coming. Last second shout out to Steve Jones. Woo!